Hey, what's up? It's your old pal, Mr. Cook. We just finished up number 6. Now we're going to do 7. And yeah, maybe 8 also. Yeah, 8 seems pretty easy. Maybe 9. You might be able to do 3 in this video. Number 7 is about continuity. So for something to be continuous, the following needs to be true. The limit at some point that you're trying to show is continuous has to exist. So as x goes to c, it has to be some number. And then also the point has to exist. So f of c has to be L. And then lastly, third one, the limit and the actual value need to be equal to each other. So if those 3 things are true, you've got continuity at a point. Okay, so if we have a piecewise function, it's really easy to tell if it's continuous or not with these 3 things if you just graph it out. So that's what I would do. I'd graph out this piecewise function. So let's see here. It looks like the only point that is really in contention is at x equals 2. So here's how I'd read the piecewise function. For x values that are less than 2, in other words, like to the left of 2, so, all the stuff over like on this side of the graph, on this side of the dotted line, are just going to be the parabola. So, it'll go through 1, 1, 0, 0, negative 1, 1. It's like, that typical parabola graph. And that 2, it'll go up to 4, 1, 2, 3, 4. So it's like right there. But here's the deal. As it gets closer and closer and closer to that, x equals 2, it doesn't actually get to that point 2. So it'll be like, if it was, it would have like a little equal sign underneath it. But since it's just x less than 2, it stops right there, just short of where that point would be. We just have an open circle there. But everywhere else, it's just, the common parabola. So it looks like that. When x is exactly at 2 for this function, we get negative 3. So if we go down 3, 1, 2, 3, when it actually is at f of 2, it's going to be this coordinate. So that's the only point, I guess, on this line that we're going to have a closed circle right there. And then the last part of it, the right-hand side of the graph, so where x is greater than 2. So in other words, like on this side of the dotted line, the graph is going to be 3x. So the way that I graph that is first find, where it gets closest to. So that'd be 2. So if I plugged in 2 for that, 3 times 2 is 6. So that's 4, 5, and 6. So that means I'm going to have another open circle like right here at 2, 6. And then from there, the slope is going to be 3. So it's going to go up 3 over 1. So it'll kind of look like this for the rest of the way. Okay, so now that I've got this this graph, this is all the proof that I would need for these 3 different conditions that I need right here, okay? Because if I draw it out, I can just use the graph to talk about the limit. Well, okay, so if we go to the first part, so the limit as x goes to 2 for this function g of x, it needs to exist, right? And, we get some value. So let's see if it exists. Well, does the limit exist at 2? Well, for the limit to exist, the left and the right-hand limits need to be the same. But you can see that as the graph is going from the left-hand side over to x equals 2, the value that it goes to, right there, is 4. So that would mean that the limit as x goes to 2 on the left-hand side for this function, it's going to end up going towards 4. And then the limit as x goes to 2 on the right-hand side, so from the right-hand side of the graph, that's the blue part. So as it goes from the right-hand side over to that point, it goes over to here, which is 6. So here's the problem. On the left and the right-hand side, we get different numbers, 4 and 6. So that means that the limit doesn't exist. So I'd write therefore, and this is how you write therefore in math terms. limit as x goes to 2 of g of x does not exist because we have two different numbers that it goes towards on the left and the right hand side. And also this means that g is not continuous or discontinuous is another way to say it at x equals 2. All right, so there you go. There's one that's like that doesn't work. For part B, is g of x continuous at 3? And let's see where it would be at 3. Well, at 3 is just over here, so it's just this point, whatever that is. Let's see what it is. So if 3 is greater than 2, so we're going to use this function here. 3 times 3 is equal to 9. So that means that that coordinate is at 3, 9. Okay, so this one is going to be continuous, and here's why. Because if I go through all the steps, let's see here. From the left-hand side, looks like it's going to 9. From the right-hand side, it's going to 9. So that means that I'd write out the following for part number 1. Does the limit as x goes to 3 of g of x exist? And let's see if that's the case. Well, if we take the limit as x goes to 3 on the left-hand side of g of x, that's definitely going to go to the 9, right? Because from the left-hand side, it goes to that point 9. And then the limit as x goes to 3 on the right-hand side also goes towards that number 9. And therefore, since the left-hand limit and the right-hand limit are the same, that means that the limit as x goes to 3 from either side of g of x is going to be equal to 9. So the limit does exist and it equals 9. So that's step 1. Step number 2, the coordinate actually does exist. It already exists. It's right there on the graph. G of 3 is equal to 9. And then lastly, step 3, the limit as x goes to 3 of the function g of x is equal to the actual value of g of 3. So since these three things are true, then I can say without any doubt that g of x is continuous at x equals 3. So there you go. That's all you need to do for number 7. All right, next up, 8. Sketch the slope field using at least 6 points in quadrant 1. Okay, no big deal. So we draw quadrant 1. That's where the x values and the y values are positive. And then we just need to pick out 6 points. Let's see here. We'll do in the quadrant. Usually you want to stick with lattice points or coordinates that have like integer values on them, the corner points. So maybe I'd use like 1, 1. And maybe like 1, maybe 2, 1 and 3, 1. And then maybe I'd use 1, 2, 2, 2, and 3, 2. There you go. That's 6 points. Okay, so I graph the points. And then I take the points and I plug them into the differential equation to draw out the slope field. So what I would do is I'd plug 1 and 1 in for x and y respectively in this equation to get that lineal element for the equation. So if I did that, -1 plus 2 times 1, that would be, 2 minus 1 is 1. So that means that I just have a slope of 1 at this coordinate. So I'm going to use red for my slope for that one. So slope of 1 would be going up 1 over 1. So it looks something like that. There you go. There's part of the slope field. Okay, and then now I plug in 2 for x and 1 for y. So -2 plus 2 times 1. So that'd be -2 plus 2, which is 0, and a slope of 0 on the coordinate 2, 1. So over 2 up. Slope of 0 look like that. And then if I plugged in 3 for x and 1 for y, I'd get -3 plus 2, which is -1. And a slope of -1 looks something like this. It's like down 1 over 1. So like that, kind of. Okay, and then I just keep repeating this process till I'm done with my slope field. I have all 6 of the different points plugged into the equation. and then their slopes are drawn on the slope field. So 1, 2 is the next one. So plugging in 1 for x would be a -1 plus 2 for y, so 2 times 2. So that'd be 4 minus 1, which is 3. So a slope of 3, this is going to be kind of tricky because I know what a slope of 1 is. So a slope of 3 is going to be like a little bit more vertical. So it'll be like that kind of. Okay, and then let's see about the next one. So if I plug in 2 for x and 2 for y, that would give me 4 minus 2, which would be 2. So a slope of 2 would maybe look like this, I guess. A little bit more than 1, 1, but a little bit less than 1, 3. And then lastly, we got, excuse me, -3 plus 4, which would be a +1. So a slope of 1 looks like the one that I have at 1, 1, so something like that. So if I had this as like a free response question on the final exam, I'd like more look at this stuff, honestly, and then obviously if you have a positive slope, I want to see it looking like that up and to the right. I wouldn't be too picky about like how accurate your slope is. Number 9. Yeah, I'll just do number 9 and then we'll stop this video and worry about another one later. So for number 9, solve the differential equation using separation of variables. That's pretty easy. So I'll move the y squared over to that side. We just did this stuff, didn't we? And then we just have an x left over, and we have a dx there. Okay, so that gives us dy, and then antiderivative of 1 over y squared. That's the same as saying y to the -2nd power, So use power rule for that, and you get y to the -1st times -1. So that's going to be a -1 over y. Antiderivative of x is 1 over 2x squared plus c. And then let's get y all by itself. So I'd like multiply by y on both sides. And then divide by all that stuff. So y is equal to -1 over all that stuff right there. Here's my general solution to the differential equation. And I don't know, I did that one pretty quick. We could probably do this one pretty fast. We could probably do all these pretty quick. Oh, what the heck. Yeah, let's just finish it up. So dy dx, so just move the y squared over again. And it looks like we can find the particular solution for this because we have an initial condition. So we'll solve for c at the end as well. So let's see here. Oops, that should be y squared. So same thing on the left-hand side, -1 over y. Then antiderivative of 2 plus x would be 2x plus 1/2 x squared plus c. And then what the heck, let's solve for the particular solution right now. So if I plug in 2 for x, and 4 for y, c is going to be equal to whatever all this stuff is. So let's see, that's 4. And then 2 squared is 4, divided by 2 is 2. So that turns into 6 overall. So if I subtract 6 from both sides, that'll be -25/24, I think. No. 25/4. Yeah, -25/4. All right, there's C. And then you can solve for y again. So multiply both sides by y. And then divide out all that stuff to get y by itself. Here's our particular solution. All right, and then the last one we'll do for this video, number 11, get y prime by itself. Well, actually, since you already have y prime there, that's like dy dx, I can just move the x over there. So that's what I'm going to do. Y prime, so y dy is equal to 3 plus x squared over x Antiderivative of y is going to be a half y squared. And then to work with this one, what I do is I divide both of the x's out. So I'd have 3 over x. And then x squared over x just turns into x. So antiderivative of 3 over x dx is going to be 3 natural log absolute value of x. Antiderivative of x is 1/2 x squared. And then I have my initial condition when x is 1, y is 2. So 1/2 2 squared is equal to 3 times the natural log of the absolute value of 1 plus 1/2 times 1 squared plus c. 1/2 of 4 is 2. And then let's see here. Natural log of 1 is 0, so that turns into a 0. And then a half. So if I subtract a half from both sides, looks like I get 3 halves is equal to c. And then you get y all by itself. I'd multiply both sides by 2. And then I take the square root of both sides. And that'd be my particular solution for this. Okay, there's number 11. And that is it. So hope you found these videos helpful. If not, go reach out to your calc teacher, get some clarity on this. I'm Mr. Cook. If you need some help, come and find me. I'm always here for help, usually before school and after school. All right, take it easy. See you in the next video. Bye-bye.